Hi everyone, welcome back to my channel. This is Xiaofu, a research enthusiastic currently working in a big tech semiconductor company. My background is in dynamics, nonlinear system, vibration, and also control. In this lecture, we are going to discuss about how we understand eigenvalue, such as stability and characteristic frequencies, eigenvectors, which show you the modal analysis that tells you what states are involved into creating this mode. And in the next lecture, we are going also to have a deep dive of eigenvalues and eigenvectors analysis. If you like my YouTube channel, please subscribe to my channel. Thank you. Let's get back to our main topic today. So as for eigenvalue, we all know that all the control system can be expressed as x dot equals to ax plus bu. And A matrix, which is a square matrix that tells us the eigenvalue or information of the entire system. So which means if you do lambda I, which I is the identity square matrix, lambda is your eigenvalue, subtract by A, get the determinant, and this is the way how you derive your eigenvalue from your A matrix. And from MATLAB, there are also a very simple way by using the syntax eg A, so that you can get the eigenvalue of your system. So what eigenvalue can tell you? So of course stability, but we are not going to show that for right now. But let's say your eigenvalue A is a real or complex number, whichever one might be possible. But looking at if you look at my previous video where we use Cayley-Hamilton theory to do a matrix exponential. So where your matrix exponential tells you not only the system response, but also you can also discretize a continuous system to a discretized system. The way how the system is going to evolve obviously depends on your eigenvalue, which is lambda I that is showing here. So lambda I can be either real and complex number, as I mentioned. If it is a complex number, of course, you have omega term, which is the one that we use it to determine the time constant and also characteristic frequency. Before we deep dive, so we have to think about some stability concepts. So here are two different concepts, which is internal and also external stability. So the difference is internal stability, you consider you don't have an input u over here. External one, you do have an input u. But whichever one you choose, you always choose a small or bounded one. So let's say you give a small perturbation which is an initial condition to your system. And ideally, small perturbation, which is an initial condition, also give you ideally small x of t. But depends on your eigenvalue, then that will depend on whether your system will eventually converge to zero or equilibrium point or not. So external one, for sure you have a non-zero input, but that's still a small input, means you also, small input give you small output, that means bounded input, you also have bounded output. So whenever we talk about stability, we always have Lyapunov over here. So Lyapunov, so sometimes before we move on, some of system, if you use Lyapunov system to determine the stability, it might be unstable in the sense of Lyapunov, but indeed it could be still stable for nonlinear system, which we would have a diagram to show and discuss. But for Lyapunov system, mainly for linear system, where you have a x dot equals to ax plus bu, and as what we know for Lyapunov is for every small quantity larger than zero, epsilon larger than zero, there always exists a delta, which is also another even smaller quantity larger than zero, such that if you give an initial condition, its magnitude larger than smaller than or equals to this small delta quantity, we conclude that for all the future time, the evolve or evolution of this x of t, the magnitude will also less than equals to the initially designed epsilon. I know this looks a little bit more, I would say, very, very not that easy to understand, but in the next slide, I'm going to show you a diagram so that you can understand it more easily. So in the absence of an input, which is your internal stability, the way how we understand it is that, okay, as long as initial condition is bounded, you should also remain a bounded output, right? That's the one we just mentioned. The system is internally stable, which is very important. One is only if and only if its eigenvalue is less than or equals to 0, which is true, because if you go back, look at, okay, how your system is going to evolve fully depends on your e to the power lambda I times t, right? If your lambda I is a positive value, then it will going to grow, right, in real time. So here, this is the way how we understand Lyapunov system. Let's say for a epsilon larger than 0, let's say epsilon, you can understand which is a larger circle that is drawn in this black solid line, and for also small delta that is drawn in this dotted line, which is in a smaller area, right? So that means if you initial condition give it to us, remain within this small circle, and it should remain bounded within this a little bit larger circle that is the diameter is defined by this epsilon, right? So which is always true for linear stable system where your eigenvalue is smaller than or equals to 0. This is very easy to understand. Well, okay, so there are cases where your Lyapunov stability will give you a different conclusion. So let's say you have a nonlinear system. I'm not going to elaborate a lot for this nonlinear system, but as we all know, nonlinear system, you have multiple equilibrium point where you can have bistable, right? Bistable system where you have two different stable state can be transitioned from one to another. It depends on your initial condition, right? Your initial condition is slightly off, then the threshold, it can eventually be attracted to a different stable state, right? So you can have two different limit cycle. Limit cycle is really for a term for nonlinear system mainly, right? So if we consider using Lyapunov's stability, let's say, we still give you a bounded small, let's say, delta within this region. It probably can converge within this region if you don't choose some specific initial condition. Well, just at the boundary, you might eventually let it, let's say, attract to another even larger or different trajectory, right? So that depends on your multi-stable system, which is generally held by nonlinear system. So eigenvalues and stability. So as we know, just now is internally one, which your input is 0. And then right now we introduce another one which is asymptotically stable. What is asymptotically stable? When I started this concept, at that beginning, I also have a confusion. But indeed it's just very simple. Asymptotic means you have damping in the system. And also you can consider your eigenvalue. So you can consider your system because of the damping will always converge to 0. That's why it said that x of t when t approach infinity, it equals to 0. It doesn't really matter what initial condition you give, right? So another one is relationship to eigenvalues. The system is internally asymptotically stable if and only if your eigenvalue is less than 0. So noted that there is no equal to 0 term here because you need a damping over 0 to make sure it can reduce the energy with time going by. If you make it equal to 0, it can be marginally stable, right? It's a different term. So right now, let's look at, okay, then what information we can get by looking at the eigenvalue, right? So eigenvalue tell you not only the system stability, as we just mentioned, larger than 0, it means your system is unstable. Smaller or equal to 0 means you have Lyapunov stable system, which is internally stable system. If you have a system less than 0 for eigenvalue, not remove the equals to 0 term, you not only have internally stable but also internally asymptotically stable, right? If you have a term that is equal to 0 only, then you have a marginally stable system, which is not covered in this slide, but I want to mention that. But you can also see that if you have an asymptotically stable system, your eigenvalue tells you the time constant, which is given by the minus inverse of your eigenvalue. But it tells you it tells you the growth and decay rate of your e to the power lambda it, which is the one that we use, and also is the one governing the transient system response that is solely compressed of your e to the power lambda I times t. And your steady state response definitely depends on your input u, but here you can see, if you don't remember the details, you can go back to my previous slides, my previous videos to check it out. For eigenvalue and characteristic oscillation frequency, this is a very interesting fact that, okay, if we just use a very simple term to describe it, if your eigenvalue is not a complex number, then you no longer have this characteristic oscillation frequency at all. So it has to make sure your eigenvalue is a complex number. And whenever it's a complex number, it always shows up as a complex conjugate altogether. And this complex number, that one tells you what is the oscillation frequency in the unit of radians. Okay, so if we use an example, so let's say you have a 12 by 12 A matrix where you will have in total 12 different eigenvalues, right? So lambda 1, lambda 2, let's say until lambda 4 are all real number which is less than 0. This we consider as overdamped system because you don't have this characteristic oscillation frequency over 0 at all. And if you also look at your other eigenvalues, if it has complex number over here, it always show up as a conjugate pair together. So whenever this happens, you have this oscillation frequency, and it's also considered an underdamped system. The question is, okay, I have so many different eigenvalues, right? Which state variables are most heavily involved in each mode, right? If I have 12 eigenvalue, I also have 12 different modes, and I don't know what state are involved in what modes, right? So how they couple together, this need to look at eigenvectors to answer this question. Okay, so for eigenvectors, let's move on a bit. So this one is a little bit of still discuss the same thing. So for system modes and modal analysis, high order systems definitely have multiple eigenvalues. This also translates to multiple time constants, multiple characteristic oscillation frequencies if you do have complex eigenvalues. And in general, the transient response of each state could include all of those time constant oscillation frequencies, right? But can we decompose the state response of the system into a set of different response? Good question, but each of which is associated with a single time constant and characteristic oscillation frequency. The answer is yes. This is the idea of modal analysis. Each of these actually the responses, motions of the system is referred to as a mode of the system. Each one of the mode can be involved by different states over there, right? It doesn't really need to be a single state. Can be coupled by different states altogether. But how do we get a eigenvector? Which is also very simple. So by using this equation, lambda I times I, which is lambda I is your eigenvalue, I is your identity matrix, A is your A matrix, Zi is your eigenvector, will be very similar to the way how we derive the eigenvalue. But first of all, you have to derive your eigenvalue to determine your eigenvector, right? So let's say we have a matrix, which is a 2 by 2 that is shown here. By calculating this determinant, makes that one equals to 0, you indeed get two different eigenvalues, which is -1, -2, right? If you plug in -1, so lambda I is your identity matrix, you get -1, 0, 0, -1, which is a 2 by 2 square matrix, and subtract by your A matrix, you get this following term. and multiply by your eigenvector, notice that if you have a 2 by 2 matrix, which means you have two different eigenvalue, you also have two different eigenvectors at the same time. They have the same quantity. And by doing that, you do a calculation, you say, okay, my eigenvector 1, which is 1 minus 1 times, which is 1 minus 1 over 0, right? So as you can say, it is indeed involved by two different states, right? X1 and X2 all together. Unless your second term is 0, then you don't have a X2 over 0, you only have X1 over 0, which is a simply decoupled. So let's look at another one. By using the same approach, you do a calculation, eventually you get your eigenvector 2 that is non-zero for both terms. So then you also have a coupled system for your mode 2, which all involve those two states together. Okay, let's start from a very easy, simple system where all of the states are decoupled. As you can see, your A term is equals to each single state over 0, no any other coupled states over 0, right? You have only A1 in first row, only A2 in second row, which is a square matrix and also diagonal square matrix. So if you do that, as we discussed in the previous slides and also lectures, so we know that if those are all constant or not a matrix, so we can either write their system response, this is your that's a transient response, and this is your steady state response, right? So that's easy for us to write it down. So if we look at it all together, you can say each one of the eigenvalue is also easy to derive, so which is A1 all the way to AN, right? So that's very easy and also simple. So if you look at this eigenvector, wow, okay, interesting. You will see that each one of the eigenvector are also only involved into a single state, and all of them seems to be decoupled, right? So this is a very, very simple system, and I will stop here for this lecture. In the next lecture, we are going to use a more complex system where your states are not simply decoupled, are coupled together, and we will see what will happen. And thank you all for watching my YouTube channel. If you like it, please subscribe to it, and we'll discuss more details for eigenvalues and eigenvectors in the next slide, in the next lectures. Thank you.